Yeah. So then the components would be independent, and the second component would have a chi-square distribution with degrees of freedom being R. The difference. So what remains to get it? So R1 plus something should be R, and so that gives you the dimension or the degrees of freedom of Q2. So R2 would be R minus R1. So the way we use that, so there is an example that you can go over yourself, and then there's a generalization. The way we used it is to prove this result that we had, that if you have the full regression model, and then you have the restricted model, you form the sum of squares of the difference of these fitted value vectors divided by sigma squared. That will have a chi-squared distribution with q degrees of freedom, where q is the number of constraints. So q, the number of constraints of the reduced model relative to the full model. And this is called, without division by sigma squared, called extra sum of squares or additional sum of squares. And this is also independent of the SSE for the full model, which is norm E squared. Yes.
So for part A, was the proof based on the quadratic forms, and then Optimality theorem when it had two parts, second half is the independence part?
No, both follow from the Cochran's theorem. So Cochran's theorem.
Cochran's theorem has two parts. The first one that gives you the distribution of Q2, and then the second one says that Q1 and Q2 are independent, or do you already have to know that in order to apply Cochran's theorem?
No, so these are both conclusions. So the key is that the interesting thing is that I just need to know that Q and Q1 have chi-square distribution.
And the other one has to be positive.
The other one has to be non-negative, yes.
Okay, and then both of the statements.
Yes, both of the
So that's where A and B come from, each of the two statements.
yes, exactly. So the interesting thing about Cochran's theorem is that it gives you two very interesting conclusions. I don't know the distribution of Q2 ahead of the time, but I just know that Q and Q1 have chi-square distributions, and Q2 is non-negative, and I know that these are quadratic forms basically. Here I'm stating that I know also that Q2 is a quadratic form, but if you do a little bit of thinking, if I know Q is a quadratic form, Q1 is a quadratic form, and I have this decomposition, Q2 has to be a quadratic form, because you can just rewrite things. So Q2 would be Q minus Q1, and then you can write it as like Y transpose some matrix times Y. So I just know that Q is chi-squared with R degrees of freedom, Q1 is chi-squared with R1 degrees of freedom, Q2 is non-negative. Then it follows that Q2 has to have a chi-square distribution. That's one of the conclusions. That's part A of that theorem, actually. And Q1 and Q2 are independent. That's part B. So this is like, if you want, this is A, this is B. The way we have it here, A gives you part A here, and B gives you part B. The key here, which I just want to emphasize, is that this holds under the null hypothesis. And the reason why it's important is, so if you recall, we have Y is equal to X beta plus epsilon. I used to call this mu. Okay, that's the mean vector. So these are in Rn. So everything is in Rn. So Y, mu, and epsilon are in Rn. So if I have a model like that, so I have the image of X, mu I know is in the image of X. Okay, because it's like X beta. But if I'm under the null, I also know that, so mu is in the image of X. But under H naught, we actually know more. So mu would be in the image of that xz, if you remember, or like LA of X in your book's notation. So mu actually would be on the smaller subspace. which I'm calling xz. Okay, so it's gonna, and the restricted subspace. Because by assumption, that restricted subspace is the set of all x betas where beta satisfy those constraints, or I just plug in beta to be x like z gamma, and then so you see that that would be xz gamma, so it would be in the image of xz. So the key is this: under null, this happens, and because this happens, when I form, so let's call this fact star. So because of fact star, what happens is when I form the residual EA, right, which is going to be I minus HA, this is going to be the projection matrix in the reduced model. So once I plug in, the reduced model would just be another regression. Okay. This, when I apply it to Y, this would be I minus HA times mu plus epsilon. If I expand it, I get I minus H times mu. So what happened to I minus H times mu? What do you guys think would happen? So mu is in the image of where HA projects. So HA projects onto this. Okay. Projects onto image of XZ, let's say you want. And mu is in the image of XZ. So what would happen? I minus HA projects onto the orthogonal complement, basically. So I have something in the image fxz, or LAX, if you want. And I'm projecting it onto the orthogonal complement of that subspace. The answer is a simple answer. 0, yes. So I get I minus HA mu plus I minus HA epsilon. This would be 0 because mu is in the image of HA, or in the image of where it projects. So HA mu would be basically mu. So you get mu minus mu. That's another way of saying it. So that's why this ends up being like this. And also E would be similar. So I minus H times Y, you get I minus H times mu plus epsilon. Mu definitely is in the image of H as well, because is in the image of X. Image of X and image of H are the same. So I minus H mu is also get to 0. Like you kill basically both of these projection matrices kill mu. So this also is going to be 0. So that's why both of these quantities will be like a projection matrix times epsilon. Okay, and they would have the distribution, which is, so the distribution of this you can verify is going to be normal, which means 0 variance sigma squared I minus HA. And the distribution is going to be normal, which means 0 variance sigma squared I minus H. We have seen this. Another way of saying it is like the top one is also a regression model. I minus HA is the projection matrix there. And that model is valid. So you'd get that. So you would get that distribution basically with 0 here if the model is valid. So the residual basically will have 0 mean if the model is valid, which means that mu is in the image of the linear model. So this is like a direct proof, but you didn't need to do this. You can just deduce it from the general results that we know that the residual vector in a linear regression model has 0 mean and variance, a covariance sigma squared I minus the H matrix for that regression if the regression model is valid. So under the null, both regression models are valid. And so you get this. If, for example, you were under the full model, but not under the restricted model, what would happen? Which one of these statements would fail? Under the alternative where this, let's say, is true, but you're not, the restricted model is not true. which one of these statements would fail. So these are still true because I'm going to fit the regression model. If I fit the regression model, this is from linear algebra. So that's how the residuals work. This statement is sort of still true because I have this in the full model, but something breaks down at some point. So the null is not true, but yeah.
Then you would no longer be the image of XZ, right?
Yes.
Just be the mu hat or the fitted mu hat A or whatever the relation is.
Yeah, so this is not going to be in the image of X, so this is not going to be 0. That's the thing. This is going to still be 0, so this goes true. This is not going to be 0. So when you do this is going to be some non-zero vector. So what happens here is that you would have this, the covariance matrix is the same, but the mean is going to be non-zero. So the mean would be whatever remains. So this mu would then be like this, and then it would have a projection onto the orthogonal complement. So that would be the component that remains. And so that part of so when you project it onto the image of that would be like the HA mu, and this would be I minus HA mu. So there is a component which is orthogonal to the image of XZ that remains, and that's going to be going there. And so when you square things, it wouldn't be like a chi-square distribution, it would be like a non-central chi-square. So there would be some non-centrality there, if you want. It's sort of clear. So if you understand what is going on, so everything almost goes through except that zero mean part is not going to be true. Sounds good? Right. The fact that we are in the image of the restricted model means that when I project like onto the orthogonal complement of these subspaces, I kill the mu. So the residuals would be 0. So the residuals would be 0 under if the model is correct. The model is not correct. One of the things that you can try is try to like assess whether the residuals look 0 mean or not. Once you fit a regression model, again, like being 0 mean is a problem that, or something that is observed if you observe many examples of the model. So when you just have one data set, it's not easy to verify whether it has 0 mean or not. But assuming that you observe multiple copies of the problem, you can assess the mean of the residual vector, and the mean of the residual vector, if it's not 0, then it means that probably the model is not correct. From one instance, you can also somehow guess, but it's a little bit harder. Sounds good? So if that's true, then we get to this picture that we had last time, and I'm not going to go over all the details. It's just one identity that we had, that triangle, the yellow triangle basically gives you this Pythagorean theorem, which we actually use a lot in calculating the f-test. So the SSE of the reduced model, which is the norm of EA squared, is SSE of the full model, norm of E squared plus extra sum of squares. This has a lot of statistical intuition packed into it. Okay, so the variance unexplained by the reduced model can be decomposed into the variance unexplained by the full model plus the part that's picked up by the full model over the reduced model. And so if you divide these by sigma squared and sigma goes in, you know that E is normal. That's the conclusion that I mentioned right there in the previous slide. So maybe do this a little bit bigger. So normal, which means 0, variance sigma squared I minus HA. So the key point here is this 0 here. Because we're under the null, this is going to be 0. And also for E, we'll have the same. So 0 means sigma squared I minus H. And so when I divide by sigma, I get rid of this sigma squared here. So I get that basically these are normal, means 0 in the projection matrix. And so the norm would have a chi-squared with rank being the projection matrix. That's the result that we have. So this will have a chi-squared distribution. Rank of the projection matrix we calculated last time, n minus the rank of HA. Rank of HA would be the dimension of that image of XZ, which is just the dimension of the image of X minus the number of constraints that we add. So we have P plus 1 minus the number of constraints. So that's the tricky part. So the chi-squared, because of theta, this is a little bit complicated. But if you understand what is going on, you get n minus because I minus HA. And H is projecting onto this reduced subspace. And this reduced subspace, the dimension is at most p plus 1 because it's inside the image of X. But it loses some of the dimensions because of the constraints. So because we have Q independent constraints, the dimension of this is going to be p plus 1 minus Q. So that's where this comes from. And then I have, for this one, we also know that it's chi-squared with n minus p plus 1 degrees of freedom. This we already see. And then this is non-negative because it's a norm of something squared. So a quadratic form chi-squared distribution, quadratic form chi-squared distribution, the remainder is non-negative, so I can apply the Cochrane's theorem. It tells me that these two components are independent, which is exactly what I want. So these are independent. I can drop the sigmas as well because sigma is constant. Okay, so the random point is norm e squared. So if these two are independent, any function of them are independent of each other. So sigma squared times this is independent of sigma squared times that. And that would just give you norm e squared is independent of norm mu hat minus mu hat a squared. Moreover, this quantity here has chi-squared with degrees of freedom being the difference between the degrees of freedom of these other two chi-squared, and we did the calculation. So if you take the difference, the degrees of freedom of this let's say left-hand side minus the degrees of freedom of the right-hand side quantity, it gives you Q. So everything simplified. So that proves the result. Okay, so questions? So there was just one tricky aspect to just make sure that these are zero means. What makes the test work and like you reject when you're not under the null is that this is not going to be zero mean. And that causes like the F test to blow up so that you'd reject. And so you now have the proof of everything except for the Cochrane's theorem, which we could have done if we would have a couple more lectures. But I leave that for some other time, maybe. Okay. So we proved everything almost except for the Cochrane's theorem, but Cochrane's theorem is sort of some advanced results, sort of advanced. But you can try your hand at trying to prove it using, again, the spectral decomposition. So write down the spectral decompositions, what you end up having to try to argue is that, so their matrices, like these matrices are simultaneously diagonalizable. Like you can use the same orthogonal matrix to diagonalize them, but that would be a little bit tricky. Okay, questions about this? This is just a summary of the proof, and so we're done with these slides. Done with quadratic forms, done with the F-test, ANOVA, and general linear hypothesis testing. No questions, then let's move on to. So there are a couple of slides remaining from this ANOVA series, which I'm going to hopefully extract. This is a separate topic. Now I'm going to talk about like what remains of chapter 4 and also chapter 5. So chapter 5 is sort of you've mostly seen, but you can go through it. Like there are examples. There's the comparison of experiments. There's these probably assigned it as homework, or hopefully varying the slope, sort of kind of regression. So the slope changes at some point. You want to test whether there is a change in the slope or not. You can do that using the F-test and also the other tests. So there is something about the design being orthogonal. Things simplify. So read that. That's just easy. So this is from chapter 4, the last part of chapter 4. I'm going to spend some time on this and then talk about multicollinearity, which is another thing, chapter 5, which is interesting. And then we're going to be done with chapters 4 and 5. So this is a result that I'm going to talk about, which is called Gauss-Markov theorem. And it's an interesting result because so far we have done like maximum likelihood, we have, or like the least squares, these all sort of things with the least squares estimate. But we did not answer whether that's the best you can do. Okay, so this is something that theoretical statisticians care about. So he came up with one estimator from somewhere, like either using maximum likelihood or least squares. Gauss sort of did it first. Let's say he came up with this. So we have like an estimator, beta, which is argmin. Let's say y minus x beta squared, which we also know is like x transpose x inverse, x transpose y, right? So it's a particular form of estimator, and I can ask whether there's anything else that it can do. So there are other types of estimators. Anyone know? So this is sometimes called ordinary least squares. Anyone knows about other types of estimators that one can do here besides the OLS? You're seeing other type of regression estimate, like estimates of the parameters.
The one like instead of squaring, you just take the absolute value.
Oh, okay.
Different.
Okay, I can do a lot of things. So I can do, for example, summation absolute value of yi minus. It would be like x beta I. Instead of square, I do the least absolute deviation, something like that they call it. So this cannot be solved in closed form, but numerically I can solve it. The objective is not differentiable, like, but it appears in robust statistics. So I don't know what this is called. Do you know what this is called? Whatever name you want to give it, that's one possible estimator. So the question is that maybe this is better than the like squaring. Why should we go with squares? Any other possibilities out there?
Power.
Yeah, you can be creative. 4 power, 6 power. So you can put anything here, right? So it gives you different type of estimators, 4th, 6th. I can take the sine if you want, like very complicated functions. So you could, in general, actually, if you go to like a more advanced course, you could have a general loss function, yi and x beta I, and you can try to minimize this. And this actually happens in generalized linear models. Let's say if you do logistic regression, you're actually solving this with some other loss. It's like called log loss or something. Binary cross entropy. Different names. General loss. So I give you a general loss. For example, like a minus b squared gives you the OLS. It could be this. It could be the 4th power. It could be something else completely. Doesn't have to be like that. So beta hat L if you want. General loss. There are other versions where you can add a penalty, right? If you remember, at some point, have you seen like penalized least squares? Less so, yeah. So you can have penalty penalized least squares. So you'd have like argmin. The loss is, this is called quadratic loss, so x beta I squared, but you add a penalty here, lambda, and penalty could be anything. So usually you add some norm here. So I'm going to write a p norm. So p norm would be like summation beta I to the p power 1 over p. So you raise to the absolute value to the power p. And take the pth root. So if you choose, for example, p equal 1, this gives you the lasso estimate. If you choose p equal to 2, okay, I'm going to do p to the p. Basically, p equal to 2 gives you ridge regression. So you get norm 2 squared. The lasso would be p equal 1, basically L1 norm, which is just the sum of the absolute values of beta. And p equal to 2 gives you basically some like think of remove the 1 over p basically. That gives you ridge regression, summation I from 1 to n beta I squared. So if you add the penalty, this has the effect which is called regularization. Anyone knows what the effect in general is of doing this? So lambda would be a positive number. How many people have seen ridge regression? Okay, less so. Okay, more people. So what is the effect of adding this penalty?
The beta is gonna tend to go to 0 once you beta become bigger.
Yeah, so once lambda, that regularization parameter lambda is called regularization parameter. Once this becomes bigger, it tends to like force beta to be closer to 0. And if lambda goes to infinity, beta, the solution would be just exactly 0. So what is the statistical effect? It's like anchoring your estimator to 0 basically. So it can't move as much, so the variance would be reduced. So the effect of regularization is that your estimate would have less variance because it tends to be closer to 0. In the end, it will be just constantly 0 variance. So your regularization will reduce will use your variance, the variance of the estimate, and also potentially has other effects. So for prediction, sometimes it improves prediction. So there is a value of lambda that has a best prediction, usually other than lambda equal to 0. But what is the drawback? So if I can reduce the variance, but something else would go up. So there's a trade-off between variance and something else. You've seen that. Bias, yes. So it's called bias variance trade-off. It allows you to do the bias variance trade-off. So what happens is when I increase lambda, my estimator is going to be basically anything other than 0. So we know that the OLS is unbiased for beta. The expectation of beta hat is equal to beta. So this is basically OLS is an example of this with lambda equal to 0. Whatever penalty you have, when lambda is equal to 0, it reduces to OLS. When lambda is bigger than 0, there's going to be a non-zero bias. So these estimators are biased. And the more I increase lambda, the more I increase the bias. So lambda goes up, variance goes down, bias goes up. Okay. The other way, lambda goes down, variance goes up, bias goes down. If you care about something called the MSE, mean squared error, it turns out the mean squared error is just the sum of the variance and bias squared. So you can try to minimize the MSE. So there's some optimal value for lambda that minimizes, like the MSE would be like something like this: beta hat minus beta squared. Rather than trying to minimize the variance alone or the bias alone, beta hat minus the true beta norm squared. If I take the expectation, this is called the MSE. So this is going to be equal to the variance of beta hat plus the bias of beta hat squared. So in some other courses, like in 200B, let's say 100B, let's say, you might have seen this. So it's slightly different than the MSCW. It's actually not exactly, it's slightly different. Yeah, so we talked about the MSC before. I'll talk about this. So SSC divided by number of user freedom. This is slightly different, maybe. It's a different notion of the MSC. Mean squared error for beta hat itself relative to the truth. This is different. So you can try to minimize this by, so if it's like 0, then beta hat has to be equal to beta always. But in general, it's not going to be 0, but you can try to minimize this. And sometimes you add a bit of bias squared plus variance of beta. So this you can prove, actually. It can be given as an exercise if you like. The bias, actually, that has to be the norm. norm of bias. Bias would be a vector. Would be something like that. Norm of bias of beta hat squared plus variance of beta hat. It would be yeah, so this is going to be troublesome. Let's say beta hat was just univariate because variance is okay. I can try to write this properly, but trace. Now I have to assign it as a homework problem. Most likely it would look like this, I hope. Trace of the covariance of beta, which is like the sum of the variances plus bias beta hat squared. But you can trade off these two. So this is like related to the variances, this is related to the bias. And so if you look at the individual coordinates, expectation of beta at I minus beta I, just it's going to be variance of beta at I plus bias of beta at I squared. So I haven't proven it, but the idea of regularization is try to minimize this by trading off bias for the variance. So I can reduce the variance. So the OLS, this part is 0. You get a particular variance. If I allow myself a little bit of bias, I might be able to reduce variance more, and so the sum might be smaller. So that's the idea of regularization, which I did not plan to go over, but just as a side note. But thinking about what is the criteria that we want to optimize, and what is the notion of optimality is what leads to this type of discussion. Whether there is a better estimator out there. That's the main question. Is the OLS the best estimator? So far, any questions? This is like more of a detour. So having a bit of bias is not necessarily bad. Just maybe I'll come back to it at some point. The idea of Gauss-Markov theorem is that this OLS has some optimality property. Among all the estimators, this is best in a particular sense. The first point is that it's blue. It's the best linear unbiased estimator. So if I restrict myself to unbiased estimators, so that rules out Ridge or Lasso. So I'm looking at things whose bias is 0. Among those whose bias is 0, and they're linear estimators, linear means a linear operator acts on the observations. So a linear operator, if you remember, can be represented by a matrix. So I apply a matrix to Y, that gives me an estimate of beta hat. I could have a different kind of matrix here. Applies to Y, gives me a different estimator. Among all possible matrices, let's say, among all possible linear estimators that are unbiased, OLS gives me the best variance, the smallest variance. Best means the smallest variance. Because everything is unbiased, we are working with unbiased estimators, we only care about the variance. Among all the linear unbiased estimators, this is best. It minimizes the variance. Smallest variance is best if you're unbiased. If you're in the Gaussian case, so this holds generally under the uncorrelated noise assumption. So if you have uncorrelated noise in regression, then this is true. So true or uncorrelated. Equal variance, basically. Both equal variance noise. So you need both uncorrelated coordinates of epsilon and they have to have the same variance. But if we assume further that the noise is Gaussian, multivariate Gaussian, then it turns out that it's really the best unbiased estimator among any kind of unbiased set of unbiased estimators. So under Gaussianity, we get a more stronger assumption, stronger conclusion. It is the best unbiased estimator. Among all unbiased estimators, you have the smallest variance. So if you pick any other estimator that's unbiased, it will have a higher variance. So that gives you some sort of a notion of optimality. There's nothing better than OLS among all unbiased estimators. If you further assume Gaussianity, then beta hat OLS is the best among all unbiased estimators, not necessarily linear ones. Okay, so linear, if we only have uncorrelatedness and equal variance for the noise. So this is basically saying covariance of epsilon, remember it's sigma squared I. If I further assume Gaussianity, which means epsilon is normal, which means 0 and variance sigma squared I, then OLS is the best unbiased estimator, has the smallest variance. Sounds good. So this is sort of a taste of what theoretical statisticians care about, or what theoretical statistics is about. It's mostly about optimality. What is best? Can we do better? It's like a competition, basically. And figuring out who gets the trophy. What estimators gets trophy. Okay? So maybe let me state the result. Maybe then you'll have questions. It's possible to state the result a little more generally. So the way I want to state it is more general because beta hat is a vector. So coordinates have variances. So beta hat I has a variance. So beta hat 1, beta hat 2. But the vector itself as a whole has a covariance matrix. So I can state the result about the covariance matrix of beta hat. So the covariance matrix of beta hat is the smallest in a particular sense. So how do we say a matrix is the smallest? Matrices are not ordered. So the way to do it is by introducing order among positive semi-definite matrices, or not positive, sorry, not among symmetric matrices. So the covariance matrix is a symmetric matrix. And if you remember positive semi-definiteness, what it means, so a matrix symmetric makes positive semi-definite if X transpose AX is non-negative for all X. Sometimes we write it like this. So this Cayley inequality means A is positive semi-definite. Okay, it's like non-negative, yes.
And is that the line on the bottom that would just be positive definite?
Where?
In your notation for A is positive semi-definite, when you just underline?
So this is the notation for being positive semi-definite.
Right. So if I take the line away, that would just be positive definite.
Oh yes, okay, yes. So yeah, people write this as well. So this when A is positive definite, yes. But we're not going to use that. Yeah. Yes. Good. And if I have this notation, then I can write A bigger than or equal to B in this notation. And interpret this as just A minus B being positive semi-definite, because that's how you interpret. When I say, for example, 4 bigger than 2, just is equivalent to saying 4 minus 2 is non-negative. So if I know how to define non-negativity, I can define order among numbers, right? So 4 bigger than 2 is just equivalent to saying 4 minus 2 is non-negative. So I know how to define a non-negative matrix in this sense. So then I write A bigger than B. Some people call this Loener order, I believe. Name after this guy, Loener. Okay, I can't pronounce his name properly, but it's a kind of order among matrices, positive among symmetric matrices. A and B need not be positive semi-definite, but the difference is positive semi-definite. If A minus B is positive semi-definite, we say that A is bigger than B. Okay, so if you understand this, yes.
So like B minus A can't be positive semi-definite.
If this holds?
Yeah.
So if this holds, then B minus A is basically negative definite. Right. So you can also write, if you want, you can say A is bigger than or equal to B, or B is less than, you can write it in this way as well. Just, you have to interpret that A minus, this is both means A minus B is positive semi-definite, or B minus A is negative definite, negative semi-definite. Negative semi-definite is just the opposite of this. This being like less than or equal to 0. Or the eigenvalues being basically all non-negative, sorry, non-positive. But just sticking with one direction is easier to think about. You can always flip the direction of the inequality by just. So if you understand this, then this is Gauss-Markov. Consider the linear regression model y is x beta plus epsilon. Noise is zero mean, noise vector, and the covariance is sigma squared in. That's the key feature. It has to have the noise has to have equal variances on the diagonal. Basically, each component has equal variances and they're uncorrelated. So the covariance matrix would look like a diagonal matrix with equal diagonal. I'll form the least squares estimate, or you can call it the OLS. This is least LSE is least squares, or you can call it ordinary least squares, other name OLS of beta. Let B hat be any other unbiased linear estimator of beta. So unbiased linear estimator means B hat can be written as some m times y. That's the linear part. And I also know that the expectation of B hat is beta for all beta. So this is some other linear estimator for some matrix M. And it's also unbiased. And then the covariance of beta hat, sorry, the covariance of B hat has to be bigger than or equal to the covariance of beta hat in this notation that we have. In other words, covariance of B hat minus the covariance of beta hat is positive semi-definite. So whenever you have a statement like that, from a statement like this, it follows, for example, that all the diagonal elements of A are bigger than or equal to all the diagonal elements of B. The reason is so that AII minus BII is the ith diagonal entry of A minus B. And we know that for the positive semi-definite matrix, the diagonal entries are non-negative. Okay, that's like a consequence of being positive semi-definite. So this gives you these set of equalities for free, but it's much stronger. So this is an implication, but not all that it implies. So if you believe that, then this statement in particular gives you that diagonal entries of the covariance of B hat, which are the variances of beta hat J, or B hat J, are bigger than or equal to the variances of beta hat J. So all the variances of the components are bigger than or equal to, because you can show this, but it tells you more. It tells you much more. Sounds good? For example, what more it gives you is that if I want to, let's say, estimate an estimate of A transpose beta, let's say this was like beta 2 minus beta 1. I can pick a particular like vector A you've seen to create, let's say, beta 2 minus beta 1, right? So I want an estimate of this. I have two candidates, A transpose beta hat from the OLS. This is like the plug-in estimator based on beta hat, and I have A transpose B hat from the other estimator. Okay, these gives me two different estimators for that quantity. From the result, we get that the variance of this plug-in estimator based on B hat is bigger than or equal to the variance of A transpose beta hat. This also follows from this fact. Follows from a star. And the way to see it is just to expand this variance. You get A transpose covariance of beta hat A. Here you get A transpose covariance of, sorry, A transpose covariance of B hat A. This is going to be A transpose covariance of beta hat A. You rearrange, you see that you get A transpose covariance of B hat minus covariance of beta hat times A. That being non-negative means the matrix is positive semi-definite, which is this statement. So this tells you that any linear combination of the coefficients have bigger variance than the corresponding linear combination. So these are all the other quantities that you try to estimate by plug-in also have bigger variance on their beta B hat than on the beta hat. So there is a strong sense in which beta hat is best. Okay, smallest variance. Small variance is good. Okay, Hopefully it shouldn't convince you that having a smaller variance is better. So Gauss-Markov only says beta hat is best within the class of linear unbiased estimators. It might be non-linear unbiased estimators that have a smaller variance, but if you assume normality, beta hat is the best unbiased estimator among all estimators, linear or non-linear. So this statement that I have here doesn't assume Gaussianity, but if you add Gaussianity, then beta hat need not be linear. It just has to be unbiased. So you can drop this assumption of linearity. So we had not beta. So this second statement follows from Kramer-Rao bound because covariance of beta hat turns out to be the inverse of the Fisher information matrix, and that's the best covariance matrix that you can have for unbiased estimators. So I'm not going to prove this. This is from like 100A. Okay. You haven't probably seen the matrix version, but so this remark too just mentioned about the consequences of A transpose beta hat is the best linear unbiased estimator of A transpose beta. Okay, questions? Yes.
If on an exam we use that shortcut from Gauss-Markov theorem to find beta hat, if you give us a new distribution, or do we have to like
What shortcut?
like if I mean like A transpose beta hat, can we just do that?
Yes, if you know, like if you use the
All the other stuff holds, we can use that.
yes, if you properly use the result, you should be able to use it. Yes, you have to know. We'll see. I'm going to give you an example where this doesn't hold, especially if the variances are unequal, and then there is a way to fix it. Okay. See if I want to prove this. Do we want to prove this result? So the proof is short, but I'm going to skip it. You can read it, and if you have questions. So the idea is that any positive semi-definite matrix can be written as Z transpose for some Z. This is equivalent, and then very quickly, so you write down like beta hat is my, expectation of beta hat is beta. You write down this expression, it tells you mx is I, okay, because the expectation of y is x beta, so you get mx beta is equal to beta for all beta, and so mx has to be I. And you calculate the covariance matrix of beta hat, you get sigma squared mm transpose. Covariance of beta hat, we know that the sigma squared x transpose x inverse, and then you form the difference. You form the difference. So actually, I form the difference m minus a. A is this guy. Right. So beta hat is ay. So you form m tilde, which is m minus a. So you form m tilde transpose. You expand. You get this expression, and ma transpose. Because you plug in mx is I, it will be AA transpose. You plug back in, you get that this quantity is just m transpose minus AA transpose. So AA transpose, basically sigma squared AA transpose is the covariance of beta hat. Sigma squared transpose is the covariance of B hat. Because this is positive semi-definite, any matrix that can be written as some matrix times that matrix transpose is positive semi-definite, this has to be positive semi-definite. So that's the proof. So it's just a few lines of algebra plus this fact that any matrix that can be written as Z transpose is positive semi-definite. This you can prove easily. And here you're going to use the unbiasedness to conclude that mx is I, and then the rest you can follow. It's a little bit tricky, but one page you can go through and try to figure out. Questions? So an interesting result here is generalized least square. So what happens if some of those assumptions fail? So one of the assumptions that can fail is let's say covariance of epsilon is not sigma squared I. how can it fail? In many different ways it can fail. So for example, if yi's are obtained by averaging some independent samples before they're given to you. So if I average like mi independent measurements, generally when you average, you reduce the variance by how many you average over. So you can think of the noise as being sort of averaged. So maybe originally they were equal variance, but now that I averaged over the measurements, I get sigma squared over mi. So this could easily happen. So you get you could like imagine that your new regression model has a covariance matrix whose still the noise are uncorrelated, but because they're averaged over different sets of measurements before given to you, they are 1 over m1, 1 over m2, 1 over mn, and so that destroys the assumption of Gauss-Markov. So the other case is you have serial correlation. So you'd have, for example, these happen in like econometrics, mostly in time series analysis. So you have yt, which depends on time, let's say sales quantity, x1t, x2t. So the like the observations are across time. So x1t could be the price of something, x2t could be how much spent on advertisement. That affects, let's say you want to see whether the price or the advertisement budget affects the sales quantity. But the noise usually is not, because it contains like some economic factors that you haven't accounted for. There's some underlying economic factor. So you're in recession or not. So the current noise and the future noise are sort of related in time series. So it's often reasonable assume to have some sort of weak dependence. So you could assume the so-called like autoregressive model, for example. How many people have seen autoregressive? Okay, so if you have taken a time series model, like a course, or if you take one, you'd see, for example, I can assume that epsilon t is some constant times the previous value plus independent noise. Here, this like phi is like a weighted average basically of the previous value and some independent noise. If phi was 0, I would get perfectly independent noise, ZT, I get like the same variance. You have the regression assumption, but if phi is not 0, let's say it's between 0 and 1. So if it's exactly 1, you get perfectly correlated noise. Epsilon t would be exactly equal to epsilon t minus 1. But if phi is between 0 and 1, but not 0, then you get correlated noise. You can sort of argue, I'll let you try to argue, that your covariance matrix would look something like this. You can try to calculate the covariance matrix, and it would not even be diagonal. So you'd have like correlations that goes down. So because phi is between 0 and 1, it dies down. So this is like correlation between epsilon at current time and at time t minus, let's say, at time n minus. It loses correlation as you move along. So, but there is some amount of correlation. So this completely destroys the assumptions that we have. But assuming that I know phi, but I don't know sigma squared, I can still do something. That's the idea of generalized linear regression. If I know, for example, these measurements, like that, then how many I averaged over? I know this part, but I don't know sigma squared. Then I'm still in business. How am I still in business? Because I can, let's say, model the noise as covariance of something sigma squared v. I'm going to assume that I know v. This may or may not be true, but if I know phi, just one number, I know the entire matrix here. If I know v, I don't know sigma squared, and also v is invertible. V has to be positive semi-definite. I can form this v negative 1/2. If you remember, there's this denoising business that we talked about. And if I apply v negative 1/2 to everything, so to y, to x, so multiply both sides by v negative 1/2, this is what we get. I'm going to call this y tilde, and I call this x tilde, and I'm going to call this epsilon tilde. If you go through the slides or just do the calculation for yourself here, I can calculate the covariance matrix of this. It's just an affine transformation. You get V inverse V minus 1/2 covariance of some V minus 1/2. V is symmetric. So you plug in V here, and these would cancel out. You get I. So you get sigma squared I. So this transformation allows me to get to a regression model in which the new noise matrix, the new noise vector has covariance matrix, which I like, sigma squared I. So this denoising process allows me to do that. I know I can do this. And so I'm going to do OLS in this new model because I know OLS in this model has the smallest variance. Okay. And if you do OLS in this model, the resulting estimator, when you look at it, is called generalized least squares. In terms of the original design, it wouldn't be the OLS. It would be something else. So once we have this new model, we can form the OLS in this new model, x tilde transpose x tilde inverse x tilde transpose. X tilde is V minus 1/2 x, the original x. So if you do the calculation, you get this result: V transpose V inverse x, the whole thing inverse, V transpose V inverse y. So you get this extra V inverse in between things. Yes.
That follows straight from the fact that x tilde is V negative 1/2 times x.
Yes. It follows exactly from this. Just plug in, do a bit of simplifications. Things are
Some of the negative 1/2 combined.
two negative 1/2s combined here. So you get x transpose V negative 1/2 transpose V is symmetric. So this not too much. No, yeah, it's just simpler than that. So x tilde transpose x tilde would be V minus 1/2 x transpose V minus 1/2 x. So what would happen to this? X transpose V minus 1/2 transpose V minus 1/2 x. V is symmetric, V minus 1/2 is symmetric. This is just V minus 1/2. So I get V minus 1/2, V minus 1/2, you get x transpose V minus 1 x. Okay. The same goes for the other one. Because y tilde is also V minus 1/2 y. If you plug in here, you get x transpose V inverse y. It's simpler than that. It's just the fact that V inverse is symmetric. Okay, so this is the OLS in the transform model, but the resulting estimator, if you view it as an estimator in the original model, this is no longer OLS. This is called generalized least squares. Okay. The advantage is that because we are doing OLS in the transform model, it has all the nice properties. So it is unbiased for beta because beta is the same for both models. So this is OLS in this model, so it has to be unbiased. So expectation of beta at GLS is beta for all beta. So it's unbiased, and the covariance I can calculate. The covariance would be sigma squared x transpose x tilde transpose x tilde inverse in the transform model. We calculate this just x transpose V inverse x inverse. Yes.
And so this is generalized because with the very first time when we assume that the covariance of epsilon is sigma squared IN, if the identity is V, then all the V's go away, and that's what we did before, right?
Yes, so it's called generalized because it's a generalization of OLS. So if V was identity, you get back to OLS. But this is more general. V could be more general. And the interesting thing is that by this transformation, this like the whitening or decorrelation transformation that we did, we get back a version of OLS in which the noise has those assumptions, and then I can do OLS, and I know that this would be the minimum variance unbiased estimator. Okay, so it's the best unbiased estimator. In particular, if I do the OLS, so what about the actual OLS in this case? So I can still do beta hat OLS, which is x transpose x inverse x transpose y. It retains some of the property, so it's unbiased. So this guy is still unbiased. You can go through the calculation and like because the model is correct, x beta is correct. So you can do the calculation, it's going to be unbiased. The covariance is still going to be, actually the covariance, the covariance you have to calculate, it's not going to be sigma squared x transpose x inverse, because the covariance of epsilon has changed. The key is that this is not the best unbiased estimator in this case, because this is not the OLS in the transform model. The transform model, so this estimator will have the smallest variance now, because this is the OLS in the case where the variances are unequal. So if you compare the variances of the OLS estimator with this one, the variances of this would be smaller. Yes.
That's covariance of beta hat with the original OLS, right?
No, so this would be like, you have to do the calculation, because the assumption when we did that was that this is sigma squared I.
So we can put OLS, that beta hat OLS, and then just beta hat after those are the same.
So yeah, this is with that OLS. I'll let you figure out the covariance. You can calculate the covariance in this case. The key is that whatever the covariance matrix is, when you compare the variances, the diagonal elements with the diagonal elements of this is going to be smaller. This is going to be a better estimator. Okay. So this is like a tricky way of applying Gauss-Markov. By doing the transformation, I can transform the problem into a problem in which I know what the best estimator is. I calculate that estimator. Now, if I go back to the original problem, the thing that comes to mind, which is the OLS in that problem, that's suboptimal. So suboptimal in this case. We'll have generally higher variance than GLS. So we can do all the tests, the stuff that we did, like F test, T test using the GLS, because it's in this, like, assuming that you understand what we're doing. Okay, so we're working with this new model. So in this new model, this is the OLS. So you can do all the things work. So for example, if you look at the residual, in the transform model, so y tilde minus x tilde beta hat GLS, that residual divided by sigma square will have chi-square distribution with n minus p minus 1 degrees of freedom. Okay. If you look at this, in terms of the original y and x, it would look like y. So okay, so if you call the residual like GLS, y minus x beta hat GLS, this is the usual residual that you calculate. This kind of residual and this one, like this norm E squared would be like E GLS transpose V inverse E GLS. So this is the usual residual that you compute. This is the residual in the transform model, and this is the one that when you divide by sigma squared has chi-squared. So if you want to compute this based on the usual residual, it would have this formula rather than the norm of the square. But this formula is the same as norm of this transform residual. So residual in the transform model. Hopefully you understand what is going on, right? So as long as you work with the transformed quantities, everything goes back to normal. When you translate it to the original x and y, they look different. So, for example, your unbiased estimate of the variance would be like this. And we can do the t-test stuff. I'll let you figure that out. And one more thing here. So what about ordinary least squares, which ignores the noise independence? It's still unbiased, but this is the result from the Gauss-Markov. So covariance of beta hat OLS would be bigger than or equal to the covariance of GLS. The other interesting part is that GLS estimator can be viewed as an optimization problem as well. So just like OLS that solves an optimization problem, you can think of the GLS estimator as solving another optimization problem. Now, instead of so beta at OLS was argmin over beta of y minus x beta squared This one replaces this quantity with this objective function. Okay, or you can rewrite it like this: V inverse y minus x beta norm squared. So beta hat GLS solve this optimization problem. Argmin beta V inverse y minus x beta squared. Or if you expand it, it would be a quadratic form, like y minus x beta transpose V inverse y minus x beta. Okay, so you can take a derivative of that and you can argue, oh, you actually know, like from this, you can see this is like V inverse transpose y is y tilde, V inverse transpose V negative 1/2 times x is x tilde. So this is really y tilde minus x tilde beta. And we know that minimizing this over beta gives you the OLS in this restricted model, which should be the GLS. So this is sort of obvious. But GLS is okay with people. Why did we do GLS? Because it has a smaller variance when the assumptions of Gauss-Markov fails, and you still know the V matrix. And then everything sort of works once you do that decorrelation business. And one last point here is that there is another version of OLS, which is called weighted least squares, which is related to all of this. The weighted least squares, it's like this is a subset of GLS. It's motivated by trying to minimize this objective function. So I try to weight each one of the observations differently. So I get wi yi minus xi transpose beta squared. If you write down this, so minimizing this would give you the weighted least squares estimator. So some of the observations I might want to downweight. I don't want to like care about those observations. Some I want to upweight. If you write down this objective, you can write it as y minus x beta transpose w1 minus x beta, and w is this weight matrix. If you compare this with this objective function that we have, you see that this objective function is more general than this, because this is like a special case where the middle matrix is diagonal. So if I compare these two, and if I can, you can see if I define V to be W inverse, I get back the GLS. Okay, so if I define a V matrix with weight being W inverse, this has nothing to do with noise, just looking at the optimization problem. The weighted least squares with this transformation is the same as GLS. So I can use the GLS sort of formalism, this or like V inverse is W to do weighted least squares. Okay, so in this particular case, all the things that we discussed. So the solution would look like this, but V inverse, you plug in W here, and that gives you the solution of weighted least square. So if you do W instead of V inverse, then you would simplify, you would get these expressions. So beta hat WS, you can write it like that. Covariance would look like this. This is just basically X transpose WX inverse X transpose WY, where W is just V inverse. This is like going to be X transpose WX. So it's just like a minor point that you can also do weighted least squares if you know GLS. It's just there's this little transformation. The main thing for us will be this GLS business, which is interesting.